Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
29.12. So we want to find the bond length for sodium chloride, given that the wavelengths for three successive transitions are these. So the first thing we want to do is convert these wavelengths into energies. So if we call this one 1, this one 2, and this one 3, delta E1 is Hc over lambda 1 is 5.381 times 10 to the negative fifth electron volts. Second one is 10, 10, 10.717 times 10 to the negative fifth electron volts. And delta E3 is 16.124 times 10 to the negative fifth electron volts. Now we note that what we've called delta E2 here is approximately twice delta E1. And we would expect these not to work out to be exact integers because of, rounding and significant digits and all that. Delta E3 over delta E1 is approximately 3, so 2.996, very close to 3. And so we know that from the way these energy levels work and knowing that delta L equals plus or minus L, we can see that these are the L equals 1 to L equals 0, L equals 2 to L equals 1, and L equals 3 to L equals 2. And so our value for delta E1, say, from the expression for these things, is going to be h bar squared over the rotational inertia of the molecule about its center of mass. So, and we know that R lives somewhere in there. So unlike some of these other problems we've done where they're diatomic molecules of a single element, sodium and chlorine are obviously different. They have different masses. So let's actually just start a new one here. So if this is our sodium, and this is our chloride ion, the center of mass is going to be closer to the chlorine because it's heavier. So this entire distance is going to be R, which is what we're looking for. And let's call this R1 for the sodium and R2 for the chlorine. So now, using what we know about just the center of mass, we can see that R1 is going to be the mass of sodium times 0 plus the mass of chlorine times R divided by the sum of the two masses, which you can just write as the mass of sodium chloride. So that's going to be 0.607 R. And then because R1 and R2 have to add up to be R, we know that R2 is just R minus R1, or 1 minus 0.607 times R. So this is 0.393 R. So now the moment of inertia is going to be the mass of our sodium times its distance squared from the center of mass, plus the mass of chlorine times its distance squared, and so just working through the numbers here, we get that this is going to be 2.317 times 10 to the negative 26th kilograms times R squared. And so now going back to what we had before, we have delta E1 equal to h bar squared over I. So I is h bar squared over delta E1, and this is, some constant with units of mass times R squared. So then R is going to be the square root of h bar squared over this constant with units of mass times delta E1. And so then putting the numbers that we know for everything in here, we get that the separation between them is 2.36 times 10 to the negative 10th meters. Or, 0.236 nanometers.